Oh, Miss Meadows, if you're recording from over here, you might get a smart comment. You know that.
Huh?
No, there's. She called you Miss Meadows. And I think we have to call you that from now on. Hey, Miss Meadows.
They have this page, not this page, but yes,
It's in there somewhere.
okay. We're probably going to go off the page for a few minutes and then we'll go back. Okay, guys and ladies, so we can get settled and started. Who has time for me? It's 10:56.
Oh, I was like, what's she talking about?
We are a few minutes behind, so let's get started. All right, this session is reactions. So we're going to be talking about reactions. I need a little feedback from the room. Have you gone back through reactions this year? Mm-hmm. Talked about reactions? Okay, so do you know your 5 main types of reactions?
Yes.
Okay, yes.
Combustion and
All right, so I think I heard them all, but let's just double check. So synthesis, decomposition, single replacement, double replacement, and combustion. Very good. All right, so here's what we're going to practice doing. I will tell you some things have changed with reactions for your test this year. The stuff that you see on these pages, this is the old format of how we did reactions on the AP exam. So the practice work, don't like be afraid of doing those, though, just because you're like, well, I don't see it exactly like this. It's okay. You need to know reactions. They just won't have them on question number 4 on the AP exam and open response part. They'll be embedded really all over your test. So they haven't taken them away. They've just not put them in one single question, and that's the only question that you have to worry so much about net ionics. You really have to still know reactions and still have to be able to write things in a net ionic equation maybe in another type of question. So knowing your solubility rules, yeah, you probably still need to know your solubility rules, all right? So let's just kind of go through some things that you already know, maybe, and let me get a feel for where you are. Have you gone back over your solubility rules, like all nitrates are soluble, acetates are soluble, group 1 are soluble, those kind of things? Okay, did you have to memorize them?
More or less.
More or less, okay. Okay, if you've got a more or less kind of thing, you're probably going to be okay, but you do need to go back and kind of keep those reviewed all the way through the year. So as you're going through all of your studies, make sure that you're understanding whenever your teacher writes an equation on the board, understand why that equation was written the way it was written. A lot of times you're going to see in the AP questions themselves, as you're taking released items for your real test, you're going to see net ionic equations used. And the first time that my students saw that this year, they kind of flipped out. It was on their first test, and they're like, I don't know what this is, and where did this go? Because we hadn't covered net ionics yet, and it was in one of the multiple choice questions. So just be aware that you will see equations written in the net ionic form, simply because that's just what is really happening in that equation. They're taking out the spectator ions. You'll understand spectator ions, okay? So those are the ones that don't even do anything, and they're writing the reaction that really happens in the container, okay? So we're going to practice a little bit just on writing some reactions before we come to this, and because I've got some demos to show you, and I want you to see if you can write a net ionic equation based on what you see. Because what you've got to do when you read a question, when you read a problem, is visualize that from something that you've seen somewhere before. So if the question says something like sodium pellets were mixed with water, understand that pellets would be referring to a solid, right? Or magnesium turnings were mixed with something else, that would be an indication of, again, a solid. So you need to be able to see those things so you have a visualization in your head whenever you're working some problems or just whenever you're answering some questions, okay? So the very first one that I've got today is, how about we do a synthesis reaction? And I know you guys and ladies have probably seen this before, but do you have a blank piece of paper somewhere in your packet? Somewhere
We have the back of the piece of
jot
paper.
this down, because maybe the back page you have to place you write some things down. Okay, because what I want you to do is I want you to write down a net ionic equation for what's happening. I want you to write down what is actually happening, write the symbols, write everything down that you can, and then I and we'll make sure that you got it right. This is a piece of magnesium. So what should you write down for that? Magnesium solid, okay? Now, coming over here to this little fume hood. If you can see this, good. If you can, you may want to turn so that you can. Maybe I can get it with. All right. Now, right now, there's actually a chemical reaction going on under the fume hood. Can you write that one down? What's burning?
O2.
Oxygen is involved in this. Anytime we burn something, oxygen is a reactant. So you can go ahead and write plus O2 after magnesium because I'm going to put this in the flame. So Mg plus O2. But also,
It's
the
methane.
second reaction, what is it?
Methane.
Methane. So what is the formula for methane?
Oh,
CH4. CH4. So if you don't know methane, that one shows up a lot in questions on the AP exam. CH4 is methane. And plus oxygen, right? CH4 plus oxygen. So you have two equations going on. Now, this one is happening before your eyes. I haven't started this one yet. What are the products of CH4 plus O2? H2O and carbon dioxide, because that's a hydrocarbon. So combustion of a hydrocarbon, if you have complete combustion, and which that's what you're going to see on these equations, you should see a complete combustion is CO2 plus H2O. What color flame do we have over here? Blue flame. If we had an orange flame, we might be producing some carbon monoxide. So there's a reason that you want to have a blue flame in lab. You don't want to be filling the room with carbon monoxide. Carbon dioxide is something that you already have in your body and you're breathing it out. But carbon monoxide, poisonous, right? Poisonous to you. So you want to keep your flame blue because a yellow flame might indicate incomplete combustion. So you might be getting some CO rather than CO2. So we're going to go over this. That's CO2 plus water. All right. Now the first equation, you have Mg plus O2, right? And so we're going to put it in the top part of the flame, and don't look directly at that. Everybody see it? Okay. All right. Okay. So now we have changed its properties. It doesn't look the same. It doesn't feel the same. I heard somebody say oxidation. Oh, good. Yes. Because we went from Mg to what charge is this now? Mg2 plus. And what is it mixed with?
O2.
It's mixed with oxygen. So correctly write your formula for the product. Okay, what's the product? What do you think the product is? We know it's Mg. Somebody said it was oxidized.
Magnesium oxide.
So if it's oxidized, it loses electrons, and I heard somebody say magnesium oxide.
Yeah.
So what is the correct formula for magnesium oxide?
MgO.
MgO. Very good. Because oxygen has what charge? 2 negative. Almost messed up on that. All right, 2 negative. All right, so that is what type of reaction? Synthesis reaction. The first reaction the second reaction was a combustion reaction. Okay. Could you also say that the magnesium plus oxygen was a combustion reaction? Did we burn it? Yes. We could say it's a combustion reaction. So just because one reaction is classified as one type doesn't mean it can't be classified as another type sometimes, especially your combustion reaction. It's not combustion of a hydrocarbon. Don't make the mistake of like, oh, well, really, you can burn it, so I should get CO2 plus H2O. Where did you have the carbon and hydrogen in that reaction? And I've had some of my kids do that before. It's like, what are you thinking? And they're like, I don't think I was. So, anyway, just make sure that you always abide by the law of conservation of mass. Matter cannot be created nor destroyed, right? Okay, let's do a decomposition reaction. I've got some calcium carbonate. Can you write the formula for calcium carbonate? Calcium carbonate. Okay, now this is a white powdery substance, so it's going to be a what? Solid. Okay. All right. So we have a solid. So far we haven't dealt with any ions, have we? No ions because we don't have any water present. So I'm going to take this. Actually, I might need a little bit more stuff. Actually, actually, let's do this. See if I can do this. Can I get your assistance? Ma'am? Yeah, sure. I'm trying to help him out. Would y'all light these candles? Here, y'all just help each other out. Alright, so I'm going to come over here. I'm going to add heat to this. Whenever I add heat to it, am I burning it? No. So one thing I'm not going to have by adding heat is plus O2, am I?
Really?
Burning it, if you have a combustion reaction, it's always plus O2. Just heating something up is not combustion. Okay? So I'm going to take this. I'm going to heat this up a little bit. So heating something up in a test tube, not combustion, what would it be? What kind of reaction would it be? Decomposition. Okay? Okay, speaking of this reaction. Okay, what do you think is being produced in this reaction? CO2. Okay. And then what would be another product? Solid calcium, you say? I don't know. Does that look metallic? No. So I don't think that's solid calcium, because calcium's a pure metal, right? Okay. Pure metals generally have a shiny light luster, generally. But what did our magnesium oxide look like a few minutes ago? It was white, powdery, and crumbly, wasn't it? Okay. So what do you think this might be? Calcium oxide. Okay. That makes sense. Because here's the thing, guys. Metal carbonates break down into carbon dioxide, that's a given, and a metal oxide. Okay? Now balance your charges. What charge does calcium have? 2. And what charge? Oxygen has 2 negative. So you should have written down CO2 plus CaO. Now let's see if this actually indeed does have some carbon dioxide that's been produced in that. I don't know, maybe not enough. Okay. Might try. Look up there and see if you see some matches on the other side of that cart. We'll try that.
Yes.
What does carbon dioxide do to a flame?
It puts it out.
It puts it out. So this is a test for carbon dioxide. If carbon dioxide is produced in this, we shouldn't see a greater flame come out of something. We should see the flame actually go out. Now I'm going to try this. My match is really far away from where I'm trying to produce some carbon dioxide. So maybe if I could go ahead and strike a match there.
Oh, Lord.
Okay.
It's gonna take a year.
Nope, you got it. Okay, just put the match right there at the mouth of the test tube. Okay, kind of go into the test tube. Oh, did you see that? Slowly put it
Oh, wait.
It's kind of going in and out because, well, you've got some carbon dioxide that's coming up there pushing the oxygen out of the test tube, and so the carbon dioxide is actually putting that out. Okay? That's a carbonate. Carbonates are always going to break down into carbon dioxide. That's going to be one of your products. Now let me look at another one. Thank you so much. Awesome. Okay, let's try another carbonate. That one we didn't see a visual change in. Still was white, solid. So this is equation number 4. This is copper carbonate. Copper carbonate. Oh, look. I think we've seen some copper stuff before today. Look at this white. I'm sorry, this is not white. Look at this solid substance. It's kind of a greenish color. Okay. Now, let's see if this one does anything. This copper carbonate, just another carbonate. So what is one of your products going to be if we heat it? Oh, good question. This is copper 2 carbonate. Very good. Wow. You need all enough information. All right. So how do copper 2 carbonate?
I can smell. No, I smell the match. That's what I'm smelling.
This is still powder. It's just loose powder. All right.
Yeah, I think that's
We have a color change in that one. Okay, what color did it
black.
change? Does that mean that it burned?
No.
No, it doesn't mean that it burned. It just means that that's the color
Reacted.
of copper oxide. Okay, that's actually the color of copper oxide. Still a solid. anything to cross out yet. No spectators. All right. There's a little bit of blue left in the middle, or green. I'm kind of shaking it around, so I might get all that out of there. Where's my friend? Did you left this back out? Okay, don't strike it yet, but you can kind of a little bit closer. So I can walk so far over there. That way you can what's your name? Dallas.
Like for kitty.
Yeah, let's kind of get out a little bit here so you can see. All right, now let's go ahead and start the match. Okay, now, what you did the last time. Oh,
can't
you'll
see
see when it went out? It went pretty quick. It went
Like
right there.
blink.
Tested. Good job, Dallas. All right, so that was just a test that we could do for the presence of carbon dioxide. So if you see that in a question or something like that, if you ever see that, then
Can't see anything now.
the flame went out. That's evidence that you had carbon dioxide produced. Okay. All right. Let me see.
There's nowhere I can put it.
So far,
Unless you wanna put it, like,
what
right
type
here.
of reaction?
Oh no, then Dallas is home. I think you can scoot it over here.
Combustion and decomposition. All right, now
Angle it a little bit. That was
let's
so
see
big,
here.
but now it's been
I'm going to take some of this calcium carbonate. So here's your next starting substance: calcium carbonate, CaCO3. Oh, I'm not supposed to tell you. I forgot. All right. Oh, let's see what I want to add this to. I want to add it to a glass. Okay, this is calcium carbonate, still calcium carbonate. Now, calcium carbonate is a big component of some things that you know a lot about, like eggshells and limestone. Okay? This is a question that I've seen a lot. If it's limestone, and limestone oftentimes is used to make some statues and gravestones sometimes, or the older ones were made out of limestone. Have you ever been to a cemetery and you're looking at the older headstones and you can't read them anymore? Yeah? What happened to them? Why are they no longer visible?
Calcium carbonate.
Calcium carbonate was eroded by what? Water. And what does the water sometimes pick up as it comes down? Well, it's going to be like acid rain. That's right. Because not only will it pick up carbon dioxide as it comes down, so water and carbon dioxide can make carbonic acid, but it might pick up even sulfur dioxide, nitrogen dioxide, and so it can make acids of like sulfurous acid, sulfuric acid, and those acids will wear away the limestone. So let's add an acid to our calcium carbonate and see what happens. Let's see. The acid I have for use is hydrochloric acid. What's the equation for hydrochloric acid? HCl. Write that down. So CaCO3 plus HCl. Now, the HCl is in solution. Okay, so what I want you to write down for HCl is what it really looks like on the paper. I mean, what it really is inside this container. Is it together? Like H and Cl together are still attached? No, they're actually not. They are going to be broken apart into ions. Hydrochloric acid is a strong acid. Okay? Have y'all learned your strong acids? Yes. And about how many of them are? Like six strong acids? Okay, so hydrochloric is one of those.
And then it's HCl.
And if you don't know these, this is a great time to write these down.
HI.
Okay, so those are all three clustered together right there on the periodic table. On the periodic table. Chlorine, bromine, iodine. Add an H to them, so hydrochloric, hydrobromic, hydro, iodic. I like to call this one a friendly acid. All right, and then you have HNO3. Do you know the name of that one? Nitric acid. Nitric acid, very good. And then we have H2, it's the only one with the 2, SO4, sulfuric acid. This is car battery acid, bad stuff.
That will dissolve the whole body.
Not good. Okay? If you ever have to mess with car battery acid, please take major precautions. Gloves, need some eye protection. Don't mess with it. It really will burn your skin off, or it will seem like it's burning your skin off. Okay? Your skin will smoke water vapor coming off of it. Because this is a water-loving compound. All right, and then one more, HClO4. Remember what this one's called? Is it chloric or perchloric? Perchloric. Now, I have seen, guys and ladies, sometimes I've seen this one listed with the group, but I've only seen it a couple times, and this is actually chloric acid. Okay? If you want to put that one down and maybe kind of, maybe, but these 6 you need to know. Now, maybe it's not so crucial right now, but you need to start putting these into your long-term memory bank, so start memorizing them. You need to know the 6 strong acids. Since we're talking about it, we've got the strong acids. Strong bases, I'm going to show you a real easy way to remember those, okay? Maybe you already know. Do you have a periodic table handy?
There's like 6 in this packet alone.
6 in that packet alone. Okay, so find a periodic table somewhere in your packet, somewhere, so if you want to share with your partner or somebody close to you, please feel free to do so. All right, I want everybody to locate group 1 elements. Group 1. Okay, what's your name? It's with the hoodie on. What's your name? Nathan. Nathan, can you point to group 1 elements up there for us? Okay, because you're kind of close. Right, gotcha. There's some type of pointer behind you. Maybe you could use one of those long objects.
Those are stands.
Okay.
Stands.
All right, great. And help him out too. If you're close right there.
Yeah, Chloe.
All right. What's your name? Chloe. Oh yeah. I'll talk to you. Okay, Chloe. All right. So we have group 1. Now, I want you on that periodic table that you're looking at, if it's available for you to write on, actually outline group 1 somehow, some way. Put a little marking around that group 1. All the way down. Actually, we'll just hit cesium. We won't do francium because francium's radioactive and we already don't ever mess with it. Okay? Okay, so start with lithium, go down to cesium. The reason I say start with lithium is hydrogen is not in group 1. It's in its own little world. Alright? Its own zone, that's right. Okay, so lithium down to cesium. Now then, I want you to curl back around in group 2. And do you see Ba, strontium, and calcium? So go up and around and do something so that you end up with something that looks a little bit like this when you finish. Okay? Now, what letter does that kind of look like? A B for bases. B for bases, especially if you take your finger and do this. Okay? B for bases. Now, when you have those metals with OH attached to the back end of them, those are your strong bases. OH attached to the back of them. So, you have LiOH. What's next? NaOH. What else? Rubidium. Rb. OH. Cesium. OH. And then we're going to go up group 2. And so you have barium.
OH.
And remember it's OH2. Calcium. OH2. Strontium. OH2. Guys, you should not forget those now. They're on your periodic table in order. And they make a B on your periodic table. Just have to put an OH behind them. Okay? Those are your, how many of them are there? How many do you count? 8. So, if you want to do 6 to 7 strong acids, 8 strong bases. That's it. Memorize those. You need to know those. Okay? That's going to be very helpful, especially when you get to acid-base chemistry in the spring. You need to know those and just have this little thing handy. It's also helpful whenever you're dealing with reactions. Okay, now, why are those important? Okay? The reason that those are important is because whenever they're in solution, they're never together with their partner. That means that HCl is always going to be H positive, Cl minus, H positive, Br minus, and so on. They don't stick together. They are strong because they ionize 100% in solution. Okay? That means they completely break apart. None of them stick together. They like water more than they like their partner. And that's just true. Water is more attractive to them than their partner is. And so water pulls them apart. Okay? All right. So we have those down. Let's go back to our reaction. Sorry, I didn't mean to spend so much time there, but I wanted you to get that. Okay, so in our reaction, we have calcium carbonate, and we have H plus and Cl minus. Y'all have that written down. Okay, so H plus and Cl minus. Now, we're going to observe, first of all, before we go too far, what type of reaction does this appear to be? Double displacement? Single displacement iron? How many double, how many singles? Double? Double, double, double? Single? Okay, it's double displacement. It's double displacement, okay? If you had it together, I think it would be easier to see it's double displacement. But I went ahead and broke it apart, okay? But it is a double displacement. Now, if you straight double displace those, let's just kind of do this in our mind. Don't write it on your paper necessarily, but you're going to have Ca getting with what? Ca getting with Cl, and you're going to have H getting with CO3. So CO3 has what charge? 2 negative, so it would be H2 CO3, right? Okay, now let's see if we have evidence for that as we do this reaction. Okay, what does it look like has happened here? I just set it on my desk. Okay, do you see anything that indicates that we might have something different happening? Let's see if I can add a little bit more. Looks like milk.
Bubbles.
Do y'all see bubbles? Okay, some of you see bubbles. What do bubbles always indicate?
A reaction.
A gas. Okay, in a reaction, I agree. But it indicates a gas. Now I'm going to step this up just a little bit. It's a little bit stronger acid, and I will not make a mess on the table. I'll make a mess over here on the floor. All right, so, okay, good, because it didn't take much of that, but you can definitely see it.
Big bubbles.
Okay, so big bubbles. What do you think those bubbles are? Gas. What kind of gas? All right, so we have some choices here. Calcium chloride. Is it calcium? Are those calcium chloride bubbles? No. All right, so we know it's not that. And I think I've used up all my stuff. It's all of them are gone. All my calcium carbonate's gone. All right, so we go to the other thing. We have the acid, H2CO3. You know anything about H2CO3?
No.
Well, we'll tell you one. Ben? All right, here's an equation that you need to put into your memory bank, okay? It is H2CO3 breaks down into H2O, water, plus carbon dioxide. Okay, so carbonic acid breaks down into water and carbon dioxide. So what do you think we just saw? What were the bubbles?
The bubbles were the CO2.
That is exactly right. The
Okay, so-
bubbles were the CO2 gas.
In the equation, would we write it as CO2 and H2O or
Yes.
H?
That is correct.
So
That is
that would
correct.
make it not necessarily a double displacement.
It is still double displacement, but you've got
Like,
two
if you
things
just
going
looked
on.
at it, it would
Right.
be the same way.
So good point. You made a very good point. It's a double displacement, but it's also a decomposition reaction. You have like two reactions going on there. Okay, so double displacement, and then the carbonic acid is breaking down into CO2 plus H2O. So let's look at our whole equation that's going on. We had the solid calcium carbonate plus hydrogen ions, chloride ions. We said calcium chloride. Now, the calcium chloride form, so where is the calcium chloride?
It's still
It's in solution, so how
liquid.
should we write that?
Ca plus.
Okay, Ca, what charge? 2 positive, plus Cl minus. All right, I see something here we can get rid of. Okay, because it's a what? Spectator. It's out of there. All right, and then our carbonic acid, H and CO3 got together, but they really didn't get together because they made this stuff. So we have water and carbon dioxide. Now, if the carbon dioxide escaped out of the flask, what's left in the container?
The water and the calcium.
The water and the calcium ions. And any other ions left? the hydrogen ions are probably left because I bet I have some excess hydrogen ions. And hey, the chloride ions are still there. We just didn't write them in our equation. Okay? They're hanging out. They watched everything happen. That's what a spectator is, right? They watch the ball game, they watch things happen, so they're still there. And a question that might be posed to you somewhere, what are the spectator ions in here? Cl minus, those are spectator ions, okay? All right. Does that kind of help you see how you might write, or you might see in that ionic equation, make it a little bit more sense maybe? I don't know. But this one equation, I'm telling y'all need to know this right here. This really never forms unless you put it under pressure. And probably, I don't know, you've got some in here right now. That Sprite, is that your Sprite? Okay. Whenever you open that Sprite, what happens? That's right, you let the pressure off. What is that breaking down? That's carbonic acid breaking down. The carbon dioxide is pumped in there under pressure. It mingles with the water, makes some carbonic acid. You open it up, release the pressure. Boom, that reaction happens. Every single time you open a carbonated beverage. I call that the Coke reaction. Because we're in the South, we call them Cokes probably, right? I do. Okay, so you can put this down, memorize this as the Coke reaction. That's what happens every time you open a Coke. Okay, so think about that. If carbon dioxide escapes from your reaction, what's happening to your Coke is it sits there with the lid off. It's flat. It's flat because the carbon dioxide's leaving. Also, look at what else it's doing. It's getting watery. It's getting more watered down, is it not? Because you're making some water whenever all the carbon dioxide is escaping. Okay? All right, let's see what else I have over here. Now, I was wanting to actually see if I could blow these candles out with this, because we had carbon dioxide, right? So let's try it. Not me blowing them out, but let's see if the flask will blow them out. Okay, can y'all see? You move it up a little bit. Oh, you're getting more nervous. All right, so let's see if I have enough carbon dioxide in here for the flask to blow them out. Okay. All right. Hey, amaze your family and friends. Guys, this is easy to make. Baking soda and vinegar produces carbon dioxide. Light a bunch of candles. If you have a ghost in the room, okay, do that at home.
I bet you
Okay, let's see what else I have. Okay, so we've gotten, we did a double displacement, right? We got a double displacement real quick. This one might not be as all that, but hey. And you probably have seen this one before. All right, I have a little bitty bit of silver nitrate in solution. Why do you think this stuff is in a brown bottle?
the light
It's
effect.
anything that's in a dark colored bottle, it's blocking the light. Okay, they started putting milk in some. I don't even know if they still do this, but a few years back, there was one company that wanted to put milk in a yellow jug because the light was passing through it. Other things they put in dark containers so that the light doesn't break it down. So silver nitrate does actually react to the light, and you can kind of see some dark spots on there. It will give little dark spots on your fingers when you get it on you whenever it reacts with the light. They have used it in film developing, so because it changes colors under reactions with light. All right, but I'm going to add a little silver nitrate. It's in solution, so go ahead and write down what you see. Silver nitrate. And so, what's the charge of silver? Plus one, good. Does it have any other charges? No. Silver only has one charge. Okay? So positive one, nitrate, so what charge? Minus one, good. Okay, so they're apart from each other, correct? Because they're not together. They're Ag positive plus NO3 negative. Now this is some salt water, so NaCl, but it's not solid, it's in solution. So you have Na positive plus Cl negative. Okay, so that's what we're starting with. Just ions swimming around. We're going to add one to the other. I wanted to see if anything changes or happens. Oh, what does that look like? What happens? It looks milky. Okay. So if something turns cloudy in the lab, what is that evidence of? Okay. But all you can see is I'm kind of shaking that around. Look, there's little chunky stuff.
Solid is formed.
A solid has formed. Okay, so from those 4 ions, we know that their first stuff that they were with wasn't going to form anything because they were clear. What has formed? Something that's solid silver chloride. That's right. So on the other side of your yield sign, with silver chloride, I see chunky stuff down at the bottom now. Salt water. Okay, so we have silver chloride. Now, did anything else form? What are the other 2 ions that are left right now?
Na and NO3.
Na and NO3. Did those 2 things get together according to your solubility rules?
No.
No, because nitrates are always soluble. Okay? Group 1 elements are always soluble, right? So those 2 form. Now, what spectators do you have?
Na and NO3.
And NO3. Cross them out. Clean up your reaction. So your final reaction,
Ag plus Cl minus yields AgCl.
that should be it. Very good. Okay, so there's your net ionic equation. And I think we've even seen a couple of those today in some of the problems that we've looked at. Maybe in some of the electrochem stuff, right? Those are net ionic equations. Okay, so cloudiness indicates a solid. Just so you know that for future reference in a question in the lab. Something turns cloudy, that's a solid. There's a fancy name for the solid. You know it? Precipitate. Very good. You might want to, if you want to write that down, an abbreviation for precipitate is PPT. And that just means a solid has formed in your container. PPT. Exactly. I'm with you on that. Okay. All right. Let's see. Oh, I have one last one because one thing we haven't done is we haven't done, well, we did this morning, but we haven't done the last time. What was that? Somebody said it. Single displacement. All right. Now, I got a little, I don't know, this sometimes happens when your chemistry teachers spend way too much time alone in the lab. They get a little creative. And so I had this little guy that has a beard. Okay.
Well then.
I was going to make a little girl that had hair, but this is an aluminum beard, and it's no shade November, so I thought I'd make a for a beard. Okay. So go ahead and write down. We're not going to react to styrofoam today, but I want you to write down the aluminum. So this is solid aluminum, Al. All right. So this guy, and could be your teacher here. I don't know. He's not young. Okay. Anyway, this guy, his beard grew out, kind of looks like my husband's beard, a little gray in it, a little old, you know. So he doesn't like the color of his beard. He's going to go to the beauty shop and do something about that.
I'm going to die.
To the beauty shop, yeah. Because at the beauty shop, get our hair done, right, girls? And they put some chemicals on our hair sometimes, do they not?
I do mine.
If you get it colored, you're getting chemicals put on your hair. That's a chemical reaction. All right, now this solution, well, I used it a little bit, so it's actually not perfect, but we're going to pretend like it's exactly, first time around. This is, what do you think? Copper. Copper, good. This has copper ions in it. I'm going to go ahead and tell you the other ion. This is copper sulfate. So what is the symbol in charge for sulfate?
SO4?
Very good. SO4, 2 negative, -2. By the way, it doesn't matter which way you write that. In some textbooks you'll see -2, and some of them you'll see 2 minuses. Don't let that be an idea. Okay? All right.
Copper is
2 minutes. All right, so we have copper sulfate, and I'm going to, what's the name? Oh, I'm sorry. I keep messing that up. It's copper 2. Copper 2 sulfate. Good question. So copper 2 sulfate, there's our little guy. He's too gray, goes to processing place. Call the beauty shop and let's see if anything might happen to him there. Alright. Yeah, maybe you should have done this one first.
Gonna go get your beard dyed, Keith?
You can get your beard dyed. right?
Exactly.
All right, now, I don't know. I'm kind of seeing, do you see anything going on there? Tiny bubbles? Oh, tiny bubbles. Tiny bubbles indication of gas, right? Now I'm going to tell you, we probably have a couple of reactions going on here. We'll just maybe focus on y'all see some tiny bubbles happening? How does it seem to be happening? Maybe you can go faster now. Okay. All right, so right now I just see some tiny, tiny little bubbles. Probably should have done this first, but you could really went countless times. Right? No. Tiny bubbles happening there. Get it back there. Keep. All right. Now, let's predict what's going to happen or what's happening inside our container. We have the aluminum and the copper. We could actually use our standard reduction potential table to figure this out. Sorry, I'm just grabbing some off the table there. Okay, if you look, guys and ladies, at your standard reduction potential table, you can predict, we only have a few more minutes, guys, so listen up. You can predict if a single displacement reaction is going to happen, okay? Because the most reactive metals are down at the bottom. So I want you to look at aluminum versus copper. Is aluminum below or above copper on this table? It's below. So the most reactive ones are down at the bottom, right? That means aluminum is more reactive than copper. So aluminum is going to kick copper out. And whenever we did that last year, we just kind of did, no charges. But basically, you have an oxidation reduction reaction taking place in this. So aluminum and copper are exchanging electrons. Aluminum is giving away its electrons to copper. So what's copper going to end up being? It's Cu2 plus, right?
The edges are turning brown.
Okay. So let's see if any changes happen to his beard.
It's like that.
Rust, what do you think it is?
It's aluminum. I mean,
It's the copper, that's right. So the copper is literally coming out of solution and trading places with the aluminum. Okay?
Perfect grade.
So his beard has changed colors from the silver now to it's kind of a brownish color. So we have solid copper that's formed. So one of your products over there is Cu, no charge. All right? The aluminum, oh, it's starting to go to town now. I knew it would in a minute. The aluminum is going from Al, solid, and it's being dropped off in the solution. So what charge does aluminum have? Positive 3, that's right. Okay, so Al has positive 3. Is the sulfate thing doing anything? Sulfate ion doing anything?
Spectator.
That's your spectator. So your reaction, not balance, but your reaction should look like this. Al plus Cu, we're going to cancel out the sulfate, goes to Al, 3 positive, plus solid Cu. Now, when you balance an equation that has differences in charges, remember you have to balance charge too. So you have to balance element and charge. So this is a 2 positive, this is a 3 positive. How many electrons or how many moles of electrons will be going through that? 6 moles, that's right, because just multiply your charges. So put a 3 here, put a 3 here, put a 2 here, and a 2 here. And we have a balanced equation both in element and charge. Okay? All right. Okay, I'm going to take his little, take him out of his processing. Oh, he's bubbling now. All right. Can y'all see a difference now? Maybe? Okay. All right, so he definitely got his hair done. Yes. I'm going to leave him in there until we go look at him at the end. Okay, let's do one or two official problems. We have about 5 minutes left. So on that page that you went to first, let's do a couple of official problems.
The machine hiccuped and gave me 2.
All right. So now that you've gotten
even.
some background again, I know that you've had this, but this was kind of a review. go ahead and do that first equation where it says a solution of sodium hydroxide is added to lead 2 nitrate. Do that one real quickly.
Practice problems, but we did them all separate, so I know it's different since they changed the test, you know, so it's kind of hard to like. They have. They've been awesome. They've been awesome.
You hear that, Miss Meadows? We're awesome. Not that we didn't already know you speak that.
Yeah, go ahead and do your net ion equation. Okay? So what are you going to get to cancel out there? She needs to go somewhere else.
Show me the pressure.
But that's just copper on the outside.
I want to like try to crunch it.
Turn them around so I can make better sure.
Okay, now guys, whenever I do these equations, a lot of times I'll go ahead and do them the straight way. I don't put them in ions yet, you know, because it's like, I know that's AQ. I know this is AQ. I know I can look at that and see that's going to be a real quick, what type of reaction? Double displacement, so Na and NO3 don't really get together, do they? Okay, and then PV and OH do get together because, hey, here's how we know they get together. Is lead hydroxide one of the strong bases? No. It's a weak base. It's not on the B. So if it's not in the B on the periodic table, it's going to stay together. All right? Every time. That's right. So this is actually going to be a solid. Now, if we clean this up from here, and if yours looks different, that's cool. But I see this is going to be there, and this is going to be there, and those are not going to be there because they're AQ on both sides. So put these with ions. They're ions, so typically you'll see the positive one written first, but it doesn't matter. You can write OH negative first if you want. So OH negative, 2 of them, because there are 2 of them in the lead hydroxide. And there's your net ionic equation. Okay? All right. Questions on that one? Or are you like, hey, I got this? Perfect. Good. Feel free to ask questions. This is your time. Okay? All right. Real quick, let's look at the next one. Y'all just tell me what type of reaction this would be. Nitric acid and calcium carbonate. Single, double, decomp. Is it double displacement? Okay. I heard double, but if you wrote out nitric acid, HNO3, and calcium carbonate, oh my goodness, I think I saw a reaction like this just a few minutes ago, didn't we?
More than one.
Okay. But it wasn't the same acid. But what do we know? Like, here's an H, here's a carbonate. What is that going to make? And what is it going to break down to? Carbon dioxide and water. So when you see those 2 pieces, that's what's going to happen. And then we have calcium and nitrate. Are they going to do anything? No, because all nitrates are soluble. All nitrates are soluble, so they're not even going to get together. So if they're not together over here, or is it? Oh, it's solid. Darn it, we got to keep it. All right, so I've got to keep the calcium here. That means I have to keep the calcium over here. And am I going to have to keep the nitrate? Yeah, because I don't have a place to. No, I get to get rid of the nitrate because it would be AQ over here. So you can have calcium, that. The hydrogen's going to have a charge. Carbonate's going to have a nothing because that's a solid. Okay?
Time's up.
Time's up. All right, guys. Well, I hope you got a little bit.